on, David.
All right. Well, I've got in my notes to start on slide 41 today. And so I'll just go ahead and go into screen sharing and run through this. Any questions before we get started? All right. So can
I have
everybody
no
see
questions, but I should tell you something funny because of these conversations. I just made a sandwich and I was thinking, oh, there's takes science to make the sandwich, but until there's proven another theory, is there a different way to make bread? Until it's proven that this is the only way that you can make bread, is there another way that you can make it?
Yeah. Yeah, there's lots of ways of making bread. I've explored a lot of them, but the way we generally make bread is the best way. So I've been lamenting a lot about science being corrupted. Talked about some of the history of that, and talked about how once you understand the logic underpinning scientific inquiry, it's really easy to begin to understand that science is not about revealing what is actually going on. But it is really good. Even though it can't reveal truth, it can reveal a lot of things that are very useful. So it is the best method for interpreting, summarizing, and applying empirical information. Empirical means stuff that you gather from your senses about the physical realm. It can be used to design systems for calculations and efficient storage and retrieval of information. So like y'all have probably heard of how taxonomists deal with how species are related into a hierarchy. And a lot of times this hierarchy of like classes, orders, and families and species are arranged to whatever extent it can be based on evolutionary theories about how they're related. And this produces a system that is parsimonious and much more effective for the compression of information. So right now I'm working on some worms that that there's several populations that are isolated in specific springs around Texas. And I'm pretty sure that these worms, these pockets of parasitic worms have been isolated and have not been interbreeding with each other for a long, long time. So all the information then that we're getting about these worms, these different populations of this worm, right now it's just one species. But we have to have some way of making sure that since these populations have been isolated, that the results of studies on this population are not just mixed in with all the rest of them. That there's a way of saying, no, this study was done on the South Contra River population. That other study was done on the San Saba River population. So the taxonomic system, though it seems real arcane and sometimes confusing, and they keep changing their minds about stuff because they're finding out new ways of joining species together into groups, it makes a very, very efficient information storage and retrieval system. And so, for instance, when I describe a new species that's new to science, like, let's see, the last one I participated in was a parasitic worm. It's a nematode off the coast of Portugal. And so I said this was a nematode. Now, when I said that said a whole lot about this worm that I did not have to go into details on. So if I describe a new species of mammal, I just say it's a mammal. And people don't have to figure out they don't ask, well, how many legs did it have? Or what was on its skin? because a mammal has hair, okay? And so there are things, when I just say it's a mammal, that says a lot about it. So see, there's a hierarchy of information storage and retrieval that is built into a lot of aspects of science. And it allows us to do predictive models, and predictive models are based on mathematical formulas. And now most of the time, we're not really predicting the future. In case you haven't been paying attention to the COVID models, you know, notice that they called this a novel coronavirus. That means they don't know what the rules are. And so all the models were wrong. Almost all of them were wrong. And any of them that were close to being right, I guarantee you it was an accident because we did not know. Now we're getting better models because we understand the virus better. But see, what we're doing is we're getting the models to line up with history, assuming that it's going to keep doing what it's been doing in the future. So the models then, based on learning about how something operates and developing mathematical models, it allows us to make plans and to intervene, to manipulate scenarios that produce a more desirable outcome most of the time. So science helps us with that. And it allows us to manipulate the physical realm. Most of us live in a building, and it's called a shelter. It's actually just a really sophisticated mammal nest, very expensive mammal nest. But it is a shelter, and in that shelter, we control things. We control so it doesn't rain inside, all right? So we don't have to worry about being out in the rain. And we get out of the weather when we come inside because we control the climate inside the house. So science allows us to do a lot of useful things like that. And it keeps social misfits like me employed and off the streets. Okay, so now here we go. All right, so hold on a minute. Let's see. I'm going to have to screen share again and go into. So I'm launching PowerPoint. So I'll stop the share and go back and reshare. There's bound to be an easier way of doing this, but I don't know how. Okay, so now I'm showing the PowerPoint running. So scientific stories are of three types. Okay, and by stories I mean narratives. So when you're reading a textbook in science, well, it's a narrative, and the narratives are of three different types. So there are stories about what is, that is, what do we think stuff is, and it's taught in lower division courses. That's where we learn jargon. So introductory courses, like when you take a introductory course in physics, you learn a whole lot of terms about stuff. Like there's a big difference between the weight of something and its mass. Now we sort of equate that as functionally identical on Earth, but if you're out in space, those are two very different things. And so anyhow, we learn a lot of that kind of stuff. And here's one of the interesting things. Well, we talk about matter, light, magnetism, electricity, and stuff. And it's taught as if it was a simple truth. So there are just simple declarative sentences that say, this is what this is. This is what this is. This is how this works. And we just look at that and say, man, they got this all figured out. And they're just statements of fact. And then stories about how the world works, how stuff operates, how do things keep happening? What are the patterns about how things operate? These are taught in upper division courses, and we're using more advanced jargon there, like junior and senior courses. The Bohr atom, it's called the model of the Bohr atom, about photons, magnetic flux, electron flow, Darwinism. Now, all of these things are myths. So this business about how the world works, they're just myths. They're narratives that we make up to explain how to expect the pattern to operate. And then there's procedures for how to. So these are what we take in engineering courses and more advanced courses, and explains how to manipulate the world. And it applies jargon to problems and solves problems and develops better ways of doing stuff and better medicine and that sort of thing. And then, but then what happens is there's like last time I was talking about this throbbing mass under the rug where there are exceptions to the rules, and those don't get taught in college. So the exceptions don't get caught. Now, when you take a PhD class at the PhD level, you start learning about this throbbing mass of exceptions that is under the rug and it's like you get in there and you say, well, wait a minute, why didn't you guys tell me about this? You take these courses at the introductory level and they have all these statements of fact as though they've got it all figured out. But then when you get into a PhD level course, you start realizing they didn't have this figured out at all. There's a whole bunch of things that don't work right. And so now what happens historically is that this mass continues to grow. And when they find a new thing that they can't figure out how to fit it into our understanding, they just shove it under the rug. And they don't talk about it in lower division courses because they don't want to say, I don't know. They don't want to say, well, we don't know how that works. But what happens is eventually some bright student just picks up the rug and looks under there and say, guys, you need to figure out a way of dealing with this. And they say, okay, you're fired or something, get out of my life. And this actually happens at scientific meetings. Somebody will stand up and say, well, what about such and such? And then they'll ridicule that person. I've seen this happen. It's happened to me. And then that person will get all wimpy, oh, so mean. And then outside in the hall, somebody else will come up to him and say, I've been finding out the same stuff. And there's something really, they're just suppressing this information. Well, there's a power structure that is built on the old understanding of how things work, and it resists change. And eventually, there is a catastrophic collapse of the old school way of thinking, and it's replaced by a new school way of thinking. And I talked earlier about the geosyncline theory and how it got replaced by plate tectonics almost overnight. Within 2 years, it was the old geosyncline theory was completely gone and was completely replaced by the plate tectonics theory. And that's called a paradigm shift or a scientific revolution. Like, for instance, theories of combustion, like what's happening when something is burning. So there was an Aristotelian explanation. There were 4 elements: air, earth, water, and fire. And we just sort of look at those guys and think, man, they were stupid. And then there were 4 traits occurring in pairs: heat versus cold, wet versus dry. So they had a narrative, they had a working narrative to explain how this stuff works. Well, that got replaced by a theory called phlogiston theory. And phlogiston says that stuff that is burnable because it's got this mysterious stuff in it called phlogiston. And it's the essence of phlogiston. And that essence is released during combustion into the air. And what is left is ash. So there's 2 things. So, and this worked. This was a workable theory for a long time. And it was better than Aristotelian. And you can extinguish fire with air that's full of phlogiston. And so, I mean, so the stuff worked. And oxidation reduction then came along. This is Priestley and Bacon and some of those guys, oxidation reduction or redox theory, and that was in 1777, and we're still using redox as a way of understanding combustion. But there are, over there under the rug, there's still a growing mass of exceptions that represent threats to a redox explanation.
David, I have a question.
Yeah.
Okay, are you familiar with the Canyon Lake when they had the flood, how it created a gorge, I guess you call it? And didn't that make some major changes in geology?
There's a theory that the canyons that you see, like out in West Texas and up in North Texas, and just, the valleys, and here's this little creek flowing through there. And you think, and you see these eroded hills, so it took a long time for that little creek to make that valley. Okay, but that's what it basically was. But then we're beginning to find out that there were a lot of really, really big floods that moved a lot of material. And so that canyon overflow was an example of that in operation. And so it added, in other words, it added a lot of fuel to the theory that a lot of these canyons were formed by major floods and some of them by catastrophic floods. So there were times when there were large lakes in ancient prehistory with, hundreds of 100 miles across or more, and big lakes, inland lakes, and they found a way to get through a mountain pass, and they cut major. So here's all this water going down to where there wasn't a river going, and cut river canyons and stuff. So and rivers, like for instance, if you look at the way the Blanco River flows out of Wimberley and it comes down and goes into Kyle. Okay, it makes a right angle turn before it goes into Kyle. Now, what flows out of, and where Onion Creek flows into, see Onion Creek, we cross Onion Creek when you go up I-35 into Austin, right at South Austin, you cross Onion Creek there. Onion Creek flows into the Colorado River. Now, Onion Creek is in a canyon. Onion Creek used to be the Blanco River. And what happened was the Blanco River was flowing like this, and there was a little creek here, and that creek kept cutting down and finally cut down, and it's called river piracy. And it captured the Blanco River flow, and now the Blanco River flows down into the San Marcos River. So there were major events like that happened in the past. Now, if that's what you're talking about, I think that's essentially what came out of that there were these major floods that occurred with surprising frequency in the past.
That's catastrophism, right?
Sir?
The change in catastrophism, the change in geology because of catastrophe versus long, slow,
that's right.
Steady, gradual change.
Yeah, and in actuality, it's both and. So now the question is, see, what happens during a revolution is we look at all those guys that were doing all this silly stuff with phlogiston, and we say, now we've got it worked out. Now we finally know the truth. The same thing happened with plate tectonics, but it's just a new theory that incorporates the new data and allows us to clean that mess out from under the rug. But then as plate tectonics redox theory, redshift theory in cosmology. As those things are applied over and over again, we start finding exceptions and we shove them under the rug. And it goes round and round and round we go. So we never get this worked out. We have to adjust our narratives as that mass of exceptions grows under the rug, and somebody finds a new way of looking at that, a new narrative that allows us to incorporate that data that was just sitting there. And now we have a more encompassing theory, and we have to rewrite textbooks and figure out new ways of teaching stuff. But we don't change the way we do stuff. We just change the narrative that we communicate about these patterns. Now, this is a sort of a segue here without a segue. So some of I'm talking now about some of the problems with scientific creationism, and the problem that we were facing about 15 or 20 years ago, when there was a major push by the evangelicals to get creation, the Genesis account of creation, taught alongside evolutionary theory in the biological classroom, especially in K through 12. Okay, so many creationists claim that evolutionary theory is corrupt and irrational because evolutionary theory requires complicated systems to arise out of simple random systems. And that is an accurate statement. That is this statement here about evolutionary theory. There's a lot of incorporation of random processes in evolutionary theory. And it doesn't make sense unless you understand what is going on here. So, and you'll hear people say, well, this is like throwing scrap parts into a barrel and expecting to pour out a Corvette, or just other statements like that. And see, this is an attempt to make evolutionary theory looks like just a sham. And this is not a reasonable response. This is not a reasonable way to argue. This is how you start quarrels, not how you resolve differences in understanding. Now, the concept of randomness, as it is used in this context, is widely misunderstood, and it's also misunderstood by many scientists. Now, complicated systems, very complicated structures can arise and do arise from what we call chaotic processes. And chaos theory, I mean, this is, maybe you haven't heard of chaos theory, but it is actually a branch of epistemology and branch of investigation about how things came to be and how things are operating. It's really, really interesting. And chaos yields order, and order yields chaos. And so I began to learn about some of these things on my own. And because I was modeling, and I was modeling host parasite systems. And I began to realize this is not going to work. I began to realize that modeling is never going to work. And it's because, see, our minds operate in linear and straight line relationships. We have to have things linear before we can say, oh, I got it now. But in reality, there are no linear relationships in the ways things operate in nature. So you've got one curve like this, and then another curve bouncing off of it, another curve bouncing off of it, and down here at the end, you've got a result. And so because of the way these curves are sort of bouncing off of each other, the slightest difference at the beginning is going to make such a major difference at the end that there's no way of predicting it, even at the 10th or 12th decimal place, if you control it to that extent. So A thorough understanding. Now, this is what got me here, this last statement here. A thorough understanding of chaos theory reveals that things are not as they seem. So this is like in The Wizard of Oz, when that old man said, "Don't just ignore the little man behind the green curtain." You know, there are things that are going on that we do not understand. And for instance, well, let's just talk about this. The butterfly effect. You may hear about this, the butterfly effect. Now, there's two origins for this term, the butterfly effect. One is that once you understand chaos theory, a butterfly on a flower in China, whether that butterfly takes off to the left or to the west or to the east, will determine the course of a hurricane in the Gulf of Mexico 2 weeks later. Right. So see, there is a very, very tiny effect that in the beginning goes down through this cascade of other effects and is magnified and ends up modifying which way a hurricane goes. So that's one of the things about chaos theory that we learn, and it's called sensitive dependence on initial conditions. Sensitive dependence on initial conditions. And the other thing is that the graphs that they make to represent this look like a butterfly wing or like an owl's mask. So this is the kind of graph that is made. And this is what's called a phase state graph. And all it means is I'm trying to point this with my finger. Okay, so these three axes are axes that represent the values of it or the state of a system. So these are values on some aspect of a system that's operating, and we're tracing where the system is regarding these three variables as time progresses. So what happens to the system is it goes around and traces back through here, and then it starts going around in this circle here. And every now and then it goes, whoop, and it goes over here, and it goes around this, and then it goes back over here, and then it goes back over here, and then it stays over here for a while. You would be astonished at how many systems you take for granted produce this butterfly effect. One is your heartbeat. So your heartbeat is not regular. In fact, if you do have a regular heartbeat, it's unhealthy. And the heartbeat can produce this pattern if you just measure the time between successive beats. There's no use to go into that, but this is a very common graph to represent. It's called a phase state system graph. And so this is a fractal. Now I'll explain the term fractal in a little bit, but it shows the behavior of a system on three axes, and the sensitive dependence on initial conditions, and small initial values are magnified over time. Now the guys that discovered this were physics grad students at I forget what university, in the University California system. And they all had PhD dissertations that they were working on with their major professor. But one of them was, he couldn't sleep one night. And he was laying there worrying about something, and his bathtub was dripping. And so he started listening to that bathtub dripping, and he started noticing that there was a pattern in the drips. You know how when you're laying awake at night and you start paying attention to stuff like this, like counting sheep or something. And so he got his watch out and started timing it, and he started seeing a pattern. So he started talking to some other students. Their professors didn't want to have anything to do with this. They said, no, you got a dissertation you got to get on. So this group of students got interested in this stuff, and they found an old analog computer down in the basement, and they started messing with it. And they would make their own faucet that they could drip. And they started studying, and they would put electric eye in there so they could actually measure the time to a fraction of a millisecond when those drops would come out. So here's these physicists up here studying this dripping faucet instead of working on their dissertations. And they made some major discoveries about chaos theory. This is with this guy listening to his bathtub dripping at night. And it made a graph like this, something similar to this. Just studying the faucet dripping was a system, very simple system that had this complex graphic. Now, this is sometimes called an owl's mask or a butterfly graph. And notice it's got two eyes here. The system never ends up in that eye or in this eye. These are called strange attractors. So this is some language. If you get into this is what strange attractors means. It means that it keeps orbiting around those two centers, but there's really nothing there attracting them. It just looks like a planet going around a black hole or something. And so these are, if you just Google, strange attractors, you'll find all kinds of fascinating stuff out there in the netherworld.
Is the strange attractors, are they like, if it was to have a resolution eventually, that those would be filled?
No, it never goes in there. But if you run this long enough, you can magnify this by looking at just a small section of these axes, and you'll see this pattern in there as well. So so this graph itself is referred to as a fractal, and I haven't defined fractal yet. I'll get to that in a minute. But some of these I'll talk about. You can magnify them, and I'm pretty sure we're going to get into that today. So
are they retracting? They're just retracting because it keeps going back and forth. They're like pulling it. It's pulling it towards that.
Well, there's nothing really there that's pulling it. It's called a strange attractor because it appears to be pulling it, but there's really nothing there. See, this is just a graph.
Okay.
And so the people studying chaos theory have discovered is that looking at graphs of how systems behave is revealing a whole nother level of understanding of how the systems are operating. And what this graph basically says is that this system is unpredictable. This system, you can never say, okay, I want to know 5 days down the road, I want to know where the dot is going to be. See, this is the tracing of a dot. So the dot is moving around, and that is, with time, the system is in different states, and that's the series of dots. The line is a series of dots. But you can predict that it'll never get outside this box, and it'll never end up in this hole. So those are things you can predict about it. But you can't predict the state of the system sometime T down the road.
We think of this somewhat like a pendulum. So it approaches one space and then to the other space, swinging back and forth.
Boy, there's some really interesting graphs that are made with pendulums. One of the things they did is they took a pendulum and they put a North Pole magnet on the end of the pendulum. And they took 3 South Pole magnets and spaced them evenly around the 3, or evenly spaced radii, so that the pendulum, if the pendulum came up here, it would be attracted away, but it would never. Well, it might hang up there. They would have it so that if you moved the pendulum up there to where it was right over that South Pole and let it go real easy, it would stay there. But they would take the pendulum, and they made the magnets, these South Pole magnets, they made them red, green, and blue. And they would And then they had this, and it was like a little bowl that the pendulum was swinging in, and they would start the pendulum over here, and they would make a mark right there where I'm going to start the pendulum right here, and I'm going to let it go. So they let it go, and it would swing down across this bowl, and then one of those magnets would pull it over this way, and then it would go this way and this way and this way. And it would eventually end up stuck on one of those magnets. And they would take whatever color that magnet was and put it on that starting spot. And then they would start it again, and they would move it over a little bit. And they would let it go, and then see what color magnet it stopped on. You wouldn't believe the graphs that they made with those colors. And some of the spots in there, where you would start it, you could never predict. Some of them you could always predict. If I started anywhere in this little spot right here, it's always going to end up on green. So they would paint that whole thing solid green. But another area down there, no matter how finely they controlled it, they could never predict where it was going to be. That's chaos. So that's chaos. So now, all of the interesting systems that we work with today are chaotic. And so the job of an engineer is actually to carve chaos out of a system so that it becomes deterministic. So see if you start the magnet, if you start the magnet anywhere in this space here, the pendulum, and let it go, and it always ends up in green, that's what we call deterministic, because it happens every time like clockwork. You start it anywhere in this patch, it'll end up on the green magnet. And so that's deterministic, but there's other places where you can start it and you can never predict, no matter how finely you control it. You can never, and that's what we call the chaos in the system. Now, weather is a lot like this. So weather, since it's based on turbulence, is chaotic. But there's sometimes when the weatherman says, okay, it's going to be 32 degrees in the morning. And you get up and you look out, and it's 32 degrees. How do you know that? Well, it's because you're in a high pressure system. And in a high pressure system, there's very little chaos. There's hardly any turbulence because the air is falling. Okay, but on a day like today, when there's clouds, we had some turbulence and some lightning a little bit earlier. They can tell you that they know that the system is developing, so they can predict several days in advance that we're probably going to have a rainy period. But they can't predict who's going to get rain, and they can't predict when it's going to happen. And so now I get this little bleeper on my phone that says it's going to start raining in 15 minutes. Well, how do they know? Because they see a big cloud over there and it's headed this way. And that's not prediction, see? I mean, that's just, you see something coming this way and how fast is it coming? So, and for this reason, they will never be able to actually predict the weather. And it's not a matter of not knowing, how having a big enough computer or anything. See, one of the things that happens is if you get enough sensors out to where you can get enough data to actually predict the weather, the sensors modify the weather. And this is something we run into all the time at a small scale or a large scale, especially at a small scale. All right, let me move on here. Now, so can order arise out of chaos? Well, we're all familiar with these images here. Well, like this is like on the beach, all right? Here's the beach. Well, what caused those rows? Well, let's see. There's waves that are coming up, and they go back and forth, and there's little sand particles there. So what in the world causes those regular rows? That's chaos. So there's a chaotic system there that is causing those rows to occur. Now, if you change the particle size or you change the viscosity of the waves, then you'll change the pattern. And it's a pretty predictable outcome. We can't, predict exactly where the waves are going to occur. And there's other places, like here's a sand dune down here. And you've heard of these places where there are these great big sand dunes that are moving, and they keep moving. And instead of just the wind blowing the sand and spreading it all out, there's this actual dune that is formed there that is moving along. And so these are some examples of ordered systems growing out of chaos. Now I know this is a really simple thing, but you see, we've got to start simple to understand that it is not irrational to say that complicated designs and order can arise out of disorder, because it happens all the time. Here's some other examples. These are cirrus clouds, and these are peculiar clouds. We don't see these very often, but notice they look a lot like breakers in the sea. Now that's a very regular pattern. Now what is happening here? Well, this is ripples in the air boundary between two temperatures that is causing these clouds to form, and it's a very regular pattern. It's arising out of the random movement of air. And here's one we're all familiar with. The snowflakes. The snowflakes are similar in that they are based on a hexagonal pattern because of, well, the theory is because of the way the molecule of water is shaped. All right. So why are they all different? Because when a snowflake is in the turbulence up there, it's going up and down and up and down and up and down. And sometimes it goes down and it gets into a warmer temperature and it melts a little bit, and then it comes up and it freezes again. And each snowflake has its own history of ups and downs, and that's what causes the snowflakes to be all these different shapes. Now see, that's a very simple random process that is producing all of this guided structure here. And now when I was a boy, my dad, well, in fact, my dad worked, he was a stonemason, and they would go out to these quarries and get stone and bring it back and sell it. And I would go around and explore, looking at rocks and stuff. And I used to see these designs like this in the rocks. So you pull a rock up in between two layers of rock, and there's this design. Well, it looks a lot like a plant. It's not a plant. It's not even a fossil of a plant. It's a mineral that is working its way between two layers of rock. And these are very ancient, but it's an iron-based mineral that is making this plant-like pattern. And it's a random process producing this very complicated structure. Here's the inverse of it right here. So these are things that are fairly common, and this is a random process producing this. And now feather structure. So there's feather structure is very complicated, and it just amazes me. I teach ornithology. And so I teach about feather development and stuff. It's just a fascinating story about how feathers develop. But they have this microscopic structure here. They have these little tiny hookies that hook over these other little structures. And so you know how you can tear a feather vein and then zip it through your fingers and it repairs itself. Well, that's because of these little hooky things. Now, when a feather starts out, it's a mass of cells. It's just a little ball of about 500 cells. Those cells divide by mitosis, and they have to divide in particular ways so that they end up in the right place in order to make a more complicated structure, which makes a more complicated structure, which makes a more complicated structure. And it turns out that the information necessary to make an entire feather, one feather on a bird, would take more information to make that feather than is in all the DNA in the bird. So it turns out that in order to make a feather from this amorphous blob of cells, all you need is some simple rules repeated over and over again. And it's amazingly intricate and yet very, very simple how this process operates, but it results in this very intricate and dependable array of parts, and all of this is cells. And I asked my students, how many of you were in the band? And usually somebody, a couple raise their hand when they were in high school. And so then I asked them about the formations on the field, you know, at halftime, how they get out there and they make these letters and designs and so forth. Well, when I was in the band, I played the tuba in high school. And so that was way back before computers. And so they would give us these cards and they would tell us, okay, you have to walk out here to the 50-yard line. And then when you get to this mark, you turn left and you walk to the 30, and then you turn around and you start tooting your horn. And of course, we'd get out there and we would follow this and we'd practice and we would always bump into each other. It was a mess. Now, with these cells, though, there's a simple set of rules. They don't all have cards that tell them which way to divide. There's a cascade of events that takes place here that has a very simple set of rules that is repeated over and over again. So it's just amazing. Now the question is, who made the rules? Who made the rules? It requires only a few genes. So seemingly random systems can produce highly ordered structures. Now here is a classical evolutionary experiment. This is called the Miller-Urey experiment. And so what they did was they made a they were trying to figure out how in the world biological chemicals could have been made without organisms. And so they made this thing, and there were some theories that said that the early atmosphere, if you look at the really, really old rocks, there was no oxygen in the atmosphere. And so it was mainly apparently methane, ammonia, and hydrogen, not exactly something you want to breathe. And so they made this self-contained thing, and they put pure water in here and boil it, and they would run the steam through this electric spark in the presence of these gases, and then they would condense it and run it back in here and boil it again. So they started out with these very simple compounds, and amazingly, they ended up with very complicated biological compounds, like adenine. Adenine is part of the DNA molecule. So that was a very complex molecule that was made by a simple random process. It was totally unexpected, totally unexpected. And it was revolutionary. Now they've done a whole bunch of other experiments by modifying the ratio of these gases or putting other gases in there, and they end up with other biological chemicals. So, and there were no organisms. This was all sterilized to begin with. So so here is a simple random process producing complicated biological, organic, in other words, biochemicals. And and I think it was in the early 20th century, there was a theory that all biological chemicals came from life, and that there were no natural processes that would make biochemicals, but this sort of upset that apple cart. So from inorganics, now, if you found something like this, Beth, you ever seen this?
Yeah, I love fractals. I used to
good, okay.
taught geometry and always integrated that. And you can also look at that. I've used fractals in teaching algebra too.
Oh, good. Excellent. Well, this is it's called a Sierpinski gasket. Now, if any of y'all found one of those, you'd probably be pretty convinced that somebody made that. This was, and you might say, oh, I'll bet that was made by one of the original natives of the American continent, because they had a lot of geometric Euclidean designs and stuff. Sort of looks like some of that those designs. Now, and I was thinking the other day, if my son found one of these, he would put it on Craigslist and sell it for $100. He could sell anything on it. It's amazing what he can, and he just sells it right away. Doesn't matter what it is. Anyhow, so suppose he sold it for $100, and they'd say, this is pretty good. I'm going to make a bunch more of these. Now, here's the way the human mind works. When we see something like this, we immediately assume this is highly ordered. Somebody had to make this. And so if we want to make some more of them, what we do is we get like a cookie cutter, a triangle-shaped cookie cutter. And we first of all cut out this big, we get a great big black equilateral triangle, and then we get a cookie cutter and cut this out, and then we get some smaller cookie cutters, and we cut this one and this one and this one. And then we get smaller ones, and we cut this one, this one, this one, this one, this one, until we get it punched down, and we got these little tiny triangles here, and we punch out these spots. And then we put it on Craigslist and sell it for $100. And then we're making money with this. But see, we have to go through this process of punching holes out with dies. And this is the way our minds work. So when we figure out how did something happen, we're thinking engineering and architecture. Factories, where we have a machine that's stamping stuff out. Now, if somebody said, no, this was made by a random process. Well, you say, get out of here. How could a random process make something like this? Well, it could make something like this way. Now, first of all, a little bit of introduction. Euclidean shapes are one of the illusions that you're probably still enjoying from your geometry class in high school. So it's easy to comprehend, like a point has one dimension. I mean, a point has 0 dimensions. A line has 1 dimension. A plane has 2 dimensions, and a solid has 3 dimensions. I grew up until I was about 50. I just assumed that was true. Now, these are called Euclidean shapes. And I thought everything that is irregular, like a rock, you look at a rock and it's, it's sort of amorphous, but I figured down at the microscopic scale, everything is still triangles and pyramids and circles and spheres and stuff. Okay, so this is a formula for a circle. And so we design Euclidean shapes. So if you have a drafting table, you're making Euclidean shapes, or you use drafting programs today. And factories mass produce Euclidean shapes. Euclidean shapes are simplified illusions, and they are not natural. So there are very few Euclidean shapes in the natural world other than crystals. So let's start this process of making one of these. So here we get this guy, and we punch triangle out of the middle. Take that, punch these other triangles out. Take that and punch these triangles out, and then punch these triangles out, and so forth. And eventually we keep getting smaller and smaller, and we end up with this thing here. That's the way we make stuff in factories. But Sierpinski figured out, I'm amazed at the way these guys, I mean, they've obviously got a lot of time on their hands, but I don't know how in the world he ever figured this out. So you make an equilateral triangle and you assign 1, 2, 3, 4, 5, 6 to the corners like this. And you get a die. That's one of a dice, a pair of dice is a die. And it's got numbers 1 through 6. So you roll the die. And suppose you get a 4. All right, you roll it again until you get another number. And then suppose it's a 3. All right, and you put dots at wherever these spots are. Now, then you change the rule and you follow this rule for the rest of the time. You roll it again, and wherever you get a point, or no, I'm sorry, back up here. So as soon as you get 2 points like this, so we got a 4 and a 3, the next rule is you find a spot halfway in between, and this is your new starting point. All right, so that's right there. All right, and then you roll the die again, and maybe we get a 3. Then you go halfway between those 2 points. That's right there. And then you roll it again and do this thousands of times. And of course, you'd make really, really tiny dots with this. And you end up with that. Random process, following simple rules. Now, the amazing thing is this is much, much more detailed than anything you can make in a factory. This is infinitely magnifiable because it's a mathematical structure. So we can take this and magnify it. So what we do is just cut off the bottom half and then expand this, cut off the bottom half. You get the picture? Infinitely. So we're down now to 100x, and it's the same. This is called self-similar fractals. And you can just go on and on at all scales. Now, when I was beginning to understand this, I was in a, goodness sakes, is it 4 o'clock already? It is, isn't it? Bob, you're muted.
Yep, 3:59. Yes, sir.
Yeah, okay. So I guess we need to quit here. But remind me next time I need to tell you about a thesis defense I interrupted when a guy was talking about Canyon Lake.
Okay, do we have any questions that you want to ask or anybody wants to ask right now?
So are you, oh, go ahead. Are you telling us that the phlogiston air fire extinguisher that I bought online is not actually any good?
No, see, here's the thing. We need to differentiate. That's a good question. We need to differentiate between what works and the narrative.
Yeah, what did we make?
In other words, the narrative is talking about things as though they were true. But we use those narratives to design fire extinguishers that actually work.
I would be worried if we're over.
And the problem is that the better the fire extinguisher works, the more we think the redox theory is the truth.
Okay.
That's the irrational part of this business about science revealing truth. And engineers can make stuff work. Man, I mean, they can really, I mean, just think about what we're doing. I mean, this private company, you know, sending these guys up in space and joining up with the space shuttle or the space station. It's just incredible. Putting these things up on Mars, millions of miles away, and running them around on Mars, drilling holes with a joystick. And so the more things start working well and predictably, the more we think we got stuff figured out. But it's irrational to do that because the stories, the narratives are made up. We actually make them up. Most scientists would say, no, we don't make them up, but they really do. And so they make up some narratives, and they start fine-tuning the narratives based on, well, that didn't work, so that must not be right. So then they'll adjust the narrative until it starts working. And then they say, well, we got it right now, until it doesn't work. And then they have to modify it again. So the narratives are continually changing, and sometimes they change catastrophic with a paradigm shift.
And sometimes they use bogus information to push the narrative. Just as an example, Uri Miller made amino acids, and that pushed the narrative forward, but they didn't make a racemically pure or racemically pure mixed, or I'm sorry, racemically pure amino acids.
Yeah.
It was a racemic mix, and they also didn't make any proteins.
No, but the see, what happened with the Uri Miller experiment was earth-shattering, though. It was a groundbreaking experiment because the paradigm at the time was that you can't make biochemicals without having an organism. That is, you can't start with inorganics and a simple process and make a complicated molecule. So
they also had a designer. Somebody designed that experiment.
Yeah, so what they were thinking, okay, there's going to be lightning going on, and so what happens when lightning strikes a pool? And was it possible now? See, what you're saying is, well, where's the critters? And
well, no, not even that, but there was an intelligent designer behind the experiment.
Yeah,
None of that happened by random. Those are all forces that were applied by somebody who put everything in motion.
Yeah, and it was, of course, happened a whole lot faster than lightning strikes would have caused stuff. So this now, see, once again, Uri Miller doesn't prove evolutionary theory as a fact because it's still a theory. So no matter what, one of these days, they're probably going to make something that behaves like an organism and reproduces. And that's just another step and about understanding how to do stuff. And so, but it still doesn't mean evolutionary theory is the truth. And it never will mean, no matter what we're able to do, it doesn't mean evolutionary theory is the truth, because as Beth knows, it's not mathematical and it's based on data. And the narrative that we have about evolutionary theory, that narrative is changing all the time. And the mechanism of Darwinism, Darwinistic natural selection, has holes in it. And I mean, in other words, there's a bunch of stuff under the rug over there that they don't get out because it's embarrassing. And so one of these days, Darwinism is going to be replaced with something else. So, but that still doesn't mean they've got the truth. So evolutionary theory is a theory. And like all scientific facts, evolutionary theory, or the various components of evolutionary theory, they all have expiration dates. And one of these days, they're going to be replaced by something else, which also has an expiration date, because that is the nature of science. So let's sort of like sum up that the main reason I'm doing this is to show that science cannot reveal truth and is not competition for the Genesis account of creation. So that, let's try to keep in mind, that is always the underlying principle that I'm trying to get across here.
Okay, thank you, David. And I guess it's after 4 now by 6 minutes. So
okay.
Scott Duncan, would you close us out in prayer, please?
Our gracious Heavenly Father, we're so thankful for David providing us with information that we can chew on over the course of the week, Lord God. And but more than that, we're thankful for your Son Jesus for sacrificing himself on the cross so we can have eternal relationship with you, Lord God. We're
Amen.
so thankful for that. And we ask you to bless David and bless the rest of us over the course of this week. We thank you in Jesus' name. Amen.
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 Thank you, brother.
All right.